A ridiculously exaggerated possible view of the Earth. The Earth we think of as a perfect sphere. We say that the radius of the Earth is 6.38 times 10 to the 6th meters, but this is an average. This is actually an average radius. And it doesn't actually really bear out. It's a good rough calculation to use, but the truth is there's a lot of factors that could affect how far away you are from the center of the Earth. One of the factors is whether you're on the equator versus on the pole. The spinning of the Earth flattens it a bit, so you're a little bit farther away from the center when you're on the equator and a little bit closer. Other things are natural landmass, where I'm going to draw this as Mount Everest. Maybe Death Valley, or the Death Valley would be here. So there are different distances away also. So how does it affect it really? Like, how does it affect the force of gravity acting on you? And the answer can be found by calculating the value of g. What this question is asking us to do is estimate g. And so g is just basically the local value of the acceleration due to gravity, or the gravitational force. And we can do that by realizing that we have two sort of equations for finding the gravitational force. One is mg, and the other one is the universal g, m1 m2 over d squared. And we can put these two together to figure it out. So what is the mass we're talking about here? We're talking about any random mass that you have. So what are the masses here? One of them is the random mass, so I'm just going to call it m, and the other one is the mass of the Earth. So m and then mass of the Earth. So you can see that these two masses are the same in these two equations. So putting these two equations together is really pretty simple. It's just mg equals g, m, mass of the Earth, divided by the distance squared. And this mass cancels out. So this is our expression for the value of calculation for g. This is how they find local g's. They determine the actual distance at a particular point. They know the mass of the Earth now, and they use the gravitational constant. So for this problem, we need to figure out what d is. Well, the height of Mount Everest is 8,850 meters, but we're not going to put that in here because remember, we want it from the center. So the distance, the radius, is 6.38 times 10 to the 6th, but then you have this additional 8850 meters. So you have to add that into this. So the distance is actually going to be 6.38 times 10 to the 6th plus 8,850 meters. And so when we do that, then we can get our calculation. So 6.38 to the 6th plus 8850, we get, so the answer we get here is 6.388850 times 10 to the 6th meters. And now we can plug that into our universal gravitational equation, or this equation that we just developed. G equals 6.67 times 10 to the negative 11. Mass of the Earth is 5.98 times 10 to the 24 divided by, and then it's 6.388850 times 10 to the 6th squared. And putting all that in, let me just do it over here. Well, I might as well put it right here. 6.67 to the negative 11 times 5.98 to the 24 divided by, and I'm just going to do this. I'm just going to hit answer squared because I already calculated the previous answer, and we get 9.77 meters per second squared. Or you can think of it as 9.77 newtons per kilogram. The idea here is that we've been using 9.8, and this is 9.77, so it rounds to 9.8. To two decimal places, 9.8 works really well. Obviously, this is 9.77. Here at Death Valley, where you're a little closer, it might be 9.81 or 82, right? But it still rounds to 9.8. So this number that we've been using is a pretty reasonable estimate for anywhere you could find yourself on the surface of the Earth.